Good day everyone! Welcome to my channel, Chris Joy TV, and welcome to Mathematics 10 class. So this is actually my very first video lesson. This is intended for modular students and online students. And of course for the parents and guardians who will be facilitating the module for their learners. Okay, so I hope you will learn something from my discussion in this video lesson. Discuss this lesson according to the what is it part of your module given by the Department of Education. So quarter 1 module 1 is about generating patterns. So before that, let us have first the rules of our session. So one, of course, you have to focus on the lesson. To find a quiet place free from distractions. So when studying, it is important that you have your study area or study corner which is conducive to learning so that you may focus. Number 3, take down notes and solve along with the teacher. So please have your module, your notebook or paper, and a pen. So the objectives of our today's session are as follows. Number 1, generate pattern from a given succession of objects, numbers, letters, or symbols. 2, find the nth term of the sequence. And lastly, write the rule for the nth term of a sequence. So let us start our discussion by having an exercise. So in this exercise, we will find the next 3 terms of each of the following. So let's say we have 3, 6, 12. Okay, so what are the next 3 terms? So first, we have to observe the pattern from the given set of numbers. So if you will notice, these numbers are multiplied by 2 to obtain the next term. So we have 3 multiplied by 2, that is 6, and 6 times 2 is 12. So meaning to say we have to continue multiplying by 2 to get the next terms. Okay, so the next terms are 24, 48, and 96. Next, 25, 17, and 9. Now these numbers are decreasing. So either we subtract or we divide these numbers to obtain the next terms. So in this case, these numbers are decreased by 8. So meaning to say we subtract 8 from the preceding term to get the next term. So 25 minus 8 is 17. 17 minus 8 is 9. So let us continue that to obtain the next terms. So those are 1, negative 7, and negative 15. So letter C, 1, 4, 9, 16. So what do you observe from these numbers? So the next terms are 25, 36, and 49. So if you will notice, these numbers are perfect squares. So square of 1, square of 2, 3, 4, 5, 6, and 7. Now, on your module, there is activity 2 wherein you cut strings once, twice, thrice, 4, up to 5 times. So I hope you already answered the questions there. So from there, were you given idea on how to generate pattern? Okay, so let us process your answers. Okay, so number 1, here is the table that represents your answers in activity 2. So we have number of cuts, that is x, and number of pieces, that is the y variable. So we cut the strings once, twice, thrice, 4 times, and 5 times. Okay, so that is the value of x. And then the number of pieces are 2, 3, 4, 5, 6. Meaning to say, when you cut the string once, there will be 2 pieces, 2 cuts, 3 pieces, 3 cuts, 4 pieces, 4 cuts, 5 pieces, and 5 cuts, 6 pieces. So what do you notice from this table? Okay, so notice that y is 1 more than the x. Okay, 1 more than the x, meaning to say we add 1 to the value of x to obtain y. Okay, so 1 plus 1 we have 2, 2 plus 1 we have 3, and so on. So we can now state our conjecture as the number of pieces in y when a string is cut x times can be computed using the formula y equals x plus 1. Okay, so take note of that. We have y equals x plus 1 as our formula. Okay, I hope you get the same answer. Okay, so using the formula y equals x plus 1, we can now solve the number of pieces of strings that can be made from 12 cuts, 24 cuts, 35, and 42 cuts. So we can now solve this without actually cutting the strings. Okay, we will just use the formula. So for 12 cuts, the value of x will be 12. So just substitute that to the given formula y equals x plus 1. So we will have y equals 12 plus 1, which is 13. Okay, so just repeat the process for 24, 35, and 42. Okay, so for 24 cuts, substitute x by 24. So we will have 24 plus 1. So the number of strings or y is 25. Okay, so for 35 cuts, we have x equals 35. So y equals 35 plus 1, which is equal to 36. And lastly, 42 cuts. So y is equal to 42 plus 1, and that is 43. So based from the activity, the number of pieces y equals x plus 1 when string is cut x times represents a sequence. Thus, the values of y, okay, which are 2, 3, 4, 5, 6, is an example of a sequence, since these numbers are in a specific order: 2, 3, 4, 5, 6. So now let us define sequence. So the word sequence means an order in which one thing follows another in succession. Okay, it is an ordered list. So for example, we have x, 2x squared, 3x cubed, 4x raised to 4, 5x raised to 5. So what would the next term be? So if you were able to observe the pattern, the numerical coefficient and the exponent are increasing by 1. And they have the same value. So we can now say that the term is 6x raised to 6. Okay, I hope you can follow. Okay, so another definition of sequence: it is a set of objects which is listed in a specific order, one after another. And each member element in the sequence is called term. So in our example, x, 2x squared, 3x cubed, 4x raised to 4, 5x raised to 5, and 6x raised to 6, those numbers are called the terms of the sequence. So the terms in a sequence can be written as a sub 1, a sub 2, a sub 3, a sub 4 up to a sub n, wherein a sub 1 is the first term, a sub 2 is the second term, a sub 3 is the third term, a sub 4 is the fourth term, and a sub n is the nth term. Now, sequences are classified as finite and infinite. So when we say finite sequence, it contains a limited number of terms. Okay, so for example, there is only 5 terms in a sequence. Okay, or there is only 8 terms in the sequence. So it means it has an end or last term. For example, days of the week. We have Sunday, Monday, Tuesday up to Saturday. Okay? So there is only 7 days in a week. So if we started here in Sunday, okay, it ends in Saturday. So Saturday is the last term of the sequence. Another example is the first 10 positive perfect squares. So from here, 10 positive perfect squares. So there is a limited number of terms. So we will have 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. So it is indicated that there is only 10 terms. So 100 is our last term. While an infinite sequence contains a countless number of terms. So we cannot identify or determine how many terms are there in an infinite sequence. So the number of terms of the sequence continues without stopping, or it has no end term. Now, the ellipsis at the end of the sequence indicates that it is infinite. So for example, we have counting numbers 1, 2, 3, 4, 5, and so on. So this is infinite because it still continues after the term 5. Okay? So there is no end term or last term. Okay? And letter B, multiples of 5. So 5, 10, 15, 20, 25, and so on. So this is up to positive infinity. Okay, if you will notice, we have ellipses at the end of our sequence. So this indicates that it does not stop with 5 and 25. It still continues. So we have no last term for these examples. So that's why these are infinite sequence. So remember, for finite sequence, there is a definite number of terms, while in infinite sequence, it has a countless or infinite number of terms. For the finite sequence, it has a last term, while in infinite sequence, it does not stop, so it has no last or end term. Okay, let us have another example. Okay, let us observe the following sequences and determine whether it is finite or infinite sequence. Okay, so letter A, 10, 20, 30, 40, 50. And this is finite, since there is a last term 50. Okay, and there is only 5 terms in the sequence. Letter B, 1, 3, 5, 7, 9, and so on. So this is an infinite sequence. Okay, because of these ellipses that indicate that the sequence continues and it has no end. And lastly, letter C, 5, 10, 15, 20, up to 100. So there is an ellipsis, but this is a finite sequence. Okay? Because we have 100 as our last term. So do not be confused. So these two examples has ellipses, but only letter B is infinite. Okay? And letter C is finite because the ellipsis is in between two terms. Okay? We still have an end term here. So I hope you can now differentiate finite and infinite sequence. So let us proceed to our next discussion. Sometimes a pattern in the sequence can be obtained and the sequence can be written using a general term. In the previous example, x, 2x squared, 3x cubed, 4x raised to 4, 5x raised to 5, and so on. Notice that each term has the same exponent and coefficient. Okay, aside from these are increasing. So we can write this sequence as a sub n equals n x raised to n. Okay, we have this numerical coefficient and exponent which are the same, okay, as the n. So what is our n? That is the number of term. Since on the first term, the exponent and coefficient is 1. For the second term, we have 2. Third term, we have 3, and so on. So those are the values of n, where a sub n is called the general or the nth term. So let us find several terms of a sequence given the general term. So in this case, we have the general term. For example, find the first 4 terms of the sequence a sub n equals 2n minus 1. So remember, when we are solving, always take note of what is asked in the problem. So in this case, we will be finding the first 4 terms. So for the solution, to find the first term, we will let n is equal to 1. Okay, and then after that, we will use this given general term a sub n equals 2n minus 1. So we will substitute n by 1. Okay, so that is 2 times 1 minus 1. Next, okay, so perform the indicated operation. 2 times 1, so we have 2, then copy minus 1. So a sub 1 is equal to 2 minus 1, which is 1. So the first term is 1. Okay, so we will just repeat the process to find the second term. So just substitute 2 for the value of n. So we will have 2 times 2 minus 1. So that is 4 minus 1, which is equal to 3. We have now the second term. For the third term, so n equals 3, again substitute and then perform the operation. So we will have 6 minus 1 equals 5. And lastly, for the fourth term, n equals 4. So a sub 4 is equal to 2 times 4 minus 1. So that is 8 minus 1 equals 7. So we now have 1, 3, 5, 7. So therefore, the first 4 terms of the sequence are 1, 3, 5, 7. Okay, let's have another example. Now, let us find the 5th to 8th term of the sequence. B sub n equals negative 1 raised to n all over n plus 1. The variable used is b. Okay, that is the same as our a sub n. So in this case, we are looking for the 5th to 8th term. So let us start with 5. So our solution, to get the 5th term, we let n is equal to 5. And then again, substitute to the given general term. Okay, so we have negative 1 raised to n all over n plus 1. So substitute n by 5. So this becomes copy negative 1 and then substitute n. So that is raised to 5 all over 5 plus 1. And then after that, we will now perform the operation. So, get the fifth power of -1, that is -1. So, remember, when we are getting the power of a negative number, there are two things that we have to remember. If the exponent is an even number, then the product will be positive. And if the exponent is an odd number, then the product is negative. So in this case, we have 5, which is odd number. So we had -1. And then 5 plus 1, that is 6. So we just simplify. So that is -1/6. So let us repeat the process. For the sixth term, we have n equals 6. Then substitute to the given formula. So that is -1 raised to 6 all over 6 plus 1. So -1 raised to 6. Okay, so even. So that is +1. And then 6 plus 1 is 7. Okay, so we have 1 over 7 for the sixth term. For the seventh term, okay, so we have -1 raised to 7. Okay, so 7 is an odd number, so therefore we have -1. And then 7 plus 1. Okay, so the denominator is 8. So -1 divided by 8, so that is -1/8. And for the eighth term, b sub 8 is equal to -1 raised to 8. Again, even, so that is +1 all over 8 plus 1, which is 9. So the answer is 1 over 9. So therefore, the 5th to 8th terms of the sequence are -1/6, +1 over 7, -1/8, and +1 over 9. Okay, so that is the process when we find the several terms of a sequence given the general term or the nth term. Now, let us do the vice versa. So, that is finding the general terms given the several terms of a sequence. Okay, so for example, write the general term of the sequence 5, 12, 19, 26, 33, and so on. So if you were able to notice, the pattern here is adding 7 to the term to obtain the next term. So from there, we can have a table that represents the term given and the pattern that we observe. So for the first term, we have 5, second term 12 up to fifth term 33, and n is our a sub n. So we always have this row for the nth term since we are looking for the general term. So for the first term, we have here only 5. Okay? To obtain the second term, we add 7. And then, add another 7 for the third term, and so on. So if you will notice, we have a repetition of addition. So we can express this as multiplication. So we have 5 plus 7 times 0. So we have here 0 since we do not add 7. For the second term, we add 7 once. So that is 7 times 1. Okay. For the third term, we have 5 plus 7 times 2. We have here 2 sevens. And then 5 plus 7 times 3 for the fourth term. 5 plus 7 times 4 for the fifth term. Okay, so for the nth term, that is 5 plus 7 plus 7 plus 7 up to plus 7. Okay, so we do not know how many 7 are we going to add since that is the nth term. So if you will notice, aside from these numbers indicate the number of times that we added 7 to 5, it is also 1 less than the term. Okay, so that is 1 minus 1, so we have 0. 2 minus 1, so we have here 1, and so on. So from there, we can now have 5 plus 7 times quantity n minus 1. Okay, so in the pattern, we have the number of times that 7 is added to 5, which is 1 less than the nth term. So that's why we represent that as n minus 1. Thus, we will now equate a sub n and the pattern that we have. So that is a sub n is equal to 5 plus 7 times quantity n minus 1. So this is now our pattern, but we have to simplify this to have our general term. Okay, so from there, we just multiplied 7 and quantity n minus 1. So we apply the distributive property. So we have a sub n equals 5 plus 7 times n is 7n. 7 times negative 1, we have negative 7. So that is minus 7. And then, if you will notice, we have 5 and negative 7, which are similar terms. So we will just combine them. So a sub n is equal to, we copy 7n. And then 5 plus negative 7, or 5 minus 7 is negative 2. So we have a sub n is equal to 7n minus 2. Therefore, we have the general term of the sequence, which is a sub n equals 7n minus 2, where n is equal to 1, 2, 3, 4, 5, and so on. So, meaning to say, if we are going to find the 10th term of the sequence, we do not have to continue the table that we did a while ago. We will just use this general term a sub n equals 7n minus 2. So, by substituting n by 10. Okay? If we are finding the, let's say, the 200th term of the sequence, so just substitute n by 200, and then you will get the 200th term of the sequence. Okay, so that is the use of our general term. Another example, write the general term of the sequence 2, 4, 8, 16, and 32, and so on. So, let us observe the pattern. These numbers are multiplied by 2 to obtain the next terms. Okay, so again, we will use a table for this example. So the first term is 2, second term is 4. So we multiply 2 by 2. For the third term, we multiply another 2, another 2 for the fourth term, and another for the fifth term. So if you will notice, since the first term is 2 and the factors that we multiply is also 2, so we can now express this as a power of 2. So for the first term, that is 2 raised to 1. For the second term, 2 times 2, so we use 2 as factors twice, so that is 2 raised to 2. For the third term, 2 raised to 3. Fourth term is 2 raised to 4. The fifth term is 2 raised to 5. Okay? So if you will notice, the power or the exponents are the same as the term. So for the nth term, we will now have 2 raised to n. So the general term of the sequence is a sub n is equal to 2 raised to n. Okay? Again, the n is 1, 2, 3, 4, 5, and so on. So if you will notice, we always start with 1. It indicates the first term. Okay, for the last example, find the general term of the sequence 1, 1/4, 1 over 9, 1 over 16, 1 over 25, and so on. So let us have our solution. So in this case, Okay, to make the terms uniform, okay, we express 1 as 1 over 1. Okay, so that we have fractions. Why 1 over 1? We can express 1 as 2 over 2, 3 over 3, 4 over 4, and so on. But we choose to write this as 1 over 1 because on the other fractions, we have 1 as their denominator so that we will have the same pattern. Okay, so aside from that, the numbers on the denominator are all perfect square. They are positive perfect squares. Okay, so for the first term, we have 1 square. 4 is the square of 2. 9 is the square of 3 or 3 square. 16 is 4 square. And 25 is 5 square. So, we now get the pattern as 1 over n square. Since the base 1, 2, 3, 4, 5 is the same as the number of terms. Okay? For the first term, we have 1, second term, 2, third term, 3, fourth term, 4, and the fifth term, 5. So therefore, for the nth term, we just use n. So that is 1 over n square. Okay? So we just express the denominators as squares. So therefore, we now have the general term of the sequence, which is a sub n equals 1 over n square. Okay, so where n is equal to 1, 2, 3, 4, 5, and so on. Okay, so I hope you learned something from our lesson, and for that, let us summarize your understandings in our lesson. So, I want you to write this on your notebook. A sequence is blank, a term is blank, a finite sequence is blank, while the infinite sequence is blank. To find the specified term or terms of a sequence when given the general term blank, to write the general term when given some terms blank. Okay, so fill in those blanks to summarize your learnings of our today's session. So remember, the only way to learn mathematics is to do mathematics. Okay, so I hope I was able to share my knowledge to you and help you with your lessons during this pandemic. So if you like my video, please click the like button, share this video, and hit the subscribe button to keep you updated on my next video lessons.